Bam! Mr. True. In this video, we're going to be doing an example where we find the equation of a tangent line to the function f of theta is equal to the sine of theta at or when theta is equal to 5 pi over 6. We're going to find the equation of the tangent line, we're going to find the equation of the normal line, and then we're going to discuss, why is it, or how are we going to use this line, equations of lines that we've been, finding since Algebra 1, tie the old in with the new. How is it going to get used in our course of calculus? And give you some links in the description below if you want to jump ahead in your calculus course and see maybe potentially how you're going to be using these tangent lines. You're also going to find a link to the homepage of my channel and website where you can find any one of the 700 plus math videos I've done so far from Algebra 1 to Calc 2 and Statistics. Alrighty then. We're going to find the line, again, that is tangent to this function at theta is equal to 5 pi over 6. What do you need to write the equation of a line? That's not going to change just because we are in calculus. You need a point and you need a slope so that you then can plug it into whatever form you like. I generally start off with point-slope form. Well, let's find the point of tangency, basically. So we have that theta, we're going to use the value of theta, which is 5 pi over 6. So let's plug 5 pi over 6 into our function and see what we have. Hopefully remember your unit circle. This won't be too terribly difficult. We haven't started talking about maybe product rule or quotient rule or especially chain rule. So we're going to be thinking about f of 5 pi over 6, and that's going to be equal to the sine of 5 pi over 6. Off the unit circle, that is going to give us an answer of 1/2. So, step 1, if you're not given a full point of tangency, find that point. So our point is going to be the value, the coordinate of 5 pi over 6, 1/2. Okay, so we have a point that our tangent line is going to go through. Now we need a slope. How are we going to do that? What did we just learn in calculus that tells us slope? Didn't we just learn how to find derivatives using the definition of a derivative or using our basic trig rules or power rule? Yes, our second step, let's pick a different color here, orange. For our second step, we're going to work on finding the slope of our tangent line, meaning what we need to do is we need to find what f prime of theta is. We need to take the derivative with respect to theta of the left-hand side. I'm writing this really for teaching purposes. Normally I just write f prime, and maybe even just write the answer to the right-hand side, but we are taking the derivative of both sides of this. So we have the derivative with respect to theta of the sine of theta. So the derivative with respect to theta of f of theta is going to be just simply f prime. And the derivative of the sine of theta with respect to theta, and as long as the variable with which we're taking the derivative with respect to is the same as our independent variable, there's no chain rule. We haven't even learned that yet maybe, but we have the cosine of theta. So we have now a function, a derivative function, which is going to tell us the slope of our original function, anywhere that we desire, as long as we remember that you cannot evaluate or find a derivative at any type of discontinuity, a sharp bend, where the original function maybe goes vertical, or the endpoint of a closed interval. So we're going to take this theta is equal to 5 pi over 6, just plug it in. We have f prime of 5 pi over 6 is equal to the cosine of 5 pi over 6, which again off of the unit circle is going to be negative square root of 3 over 2. Yes, we're in advanced calculus, but what you need to write the equation of line is not going to change from pre-algebra or algebra 1, wherever you first learned how to find the equation of a line. I'm sure that was algebra 1. So let's take step 3 and I'd like to grab it in color, but the green and blue sometimes is a little bit hard to see. So step 3, we're going to take that point of 5 pi over 6 and 1/2, take that slope that we just found of negative square root of 3 over 2 and just go back to our point slope form. The point slope form of a line, of course, is y minus y sub 1. So we have y minus 1/2 is equal to m. We just found that. The instantaneous rate of change for the equation or function f of theta is equal to the sine of theta. That instantaneous rate of change is negative square root of 3 over 2. The slope of the sine function when theta is equal to 5 pi over 6. Then we have x minus x sub 1. So we have x minus 5 pi over 6. And we're going to go ahead and keep all this in exact format. So distributing that negative square root of 3 over 2 through, we're going to have y minus 1/2 is equal to negative square root of 3 over 2x. We have negative times negative, which is positive, so plus 5 pi times square root of 3, of course, just 5 pi square root of 3. Multiplying our denominators in here, we have 2 times 6, which is equal to 12. AP is going to want the equation of your tangent line in slope-intercept form. I also teach IB, International Baccalaureate Program, and a lot of times they're happy with the equation of their lines in point-slope form. So just put the equation of your tangent line in whatever form your teacher is requesting or requiring. We're going to undo the minus 1/2 over here with the y, of course, by adding both sides by 1/2. We're going to then need to find a common denominator, so we're going to multiply by 1/2 by 6 in the numerator and 6 in the denominator, a form of 1. And we have y is equal to negative square root of 3 over 2x plus, we've got 5 pi square root of 3 plus 6 over 12. And this is the equation of the line which is tangent to the function f of theta is equal to sine of theta at or when theta is equal to 5 pi over 6. Now, I'm going to write this over here on the left-hand side, and I will graph we'll be looking at the graph of sine and the graph of the tangent line and the normal line before we go on and again discuss when you may be using these tangent lines later on in this course and how you're going to be using them. So let me get this out of the way. Sometimes we're not going to be asked for the equation of a tangent line. We're going to be asked for the equation of a normal line. Now, the difference between a normal line and a tangent line is at the point of tangency, the equation of the tangent line, well, it's going to have the same slope as the slope of the function. Or effectively, we're kind of, if you think about that definition of a derivative and how we have 2 points that are becoming ever closer together as we let delta x approach 0, we're using the slope between 2 points that are infinitely close. We're kind of using the slope of the tangent line to estimate the slope of the function at some given value. A normal line is just simply perpendicular. So instead of a line which is parallel to the function at a particular domain value, we're looking for the equation of a line which is perpendicular. Oh, okay, so for the normal line, we have, and I'll do this in orange, for our normal line, we're still working with that same point of tangency, which for some reason I erased. 5 pi over 6 and 1/2. But for the normal line and understanding now that it's perpendicular, our perpendicular slope is the opposite reciprocal of the, slope of the tangent line, or the slope of that function at some particular value for which of domain, 5 pi over 6. So the opposite reciprocal of negative square root of 3 over 2 is positive 2 over square root of 3. Of course, you're going to rationalize that denominator, or at least I'm going to. So we have a point that we're going to use to find the equation of the normal line, which again is 5 pi over 6 and 1/2, and the perpendicular slope is, again, 2 square root of 3 over 3. Point slope form of a line, y minus y sub 1, so y minus 1/2 is equal to m, 2 square root of 3 over 3. times x minus x sub 1, x minus 5 pi over 6. We're going to distribute that slope, which is now positive, to square root of 3 over 3 through the parentheses, yielding us y minus 1/2 is equal to 2 square root of 3 over 3x minus, because of course it's positive times negative, 2 times 5 is 10, so 10 pi square root of 3 over, we've got 3 times 6 is 18. And we need to find a common denominator as we go through the process of undoing the minus 1/2 that's over here with the y. We're going to add both sides by 1/2. We need a common denominator between this term that doesn't have the variable of x in it and our 1/2. So we're going to multiply the numerator and denominator by 9. And that is going to give us a normal line, which is y is equal to 2 square root of 3 over 3x. And I'm going to write plus and bring these two terms together. We have a negative 10 pi square root of 3 and a positive 9. And I want to write this as an addition. So I'm going to write that 9, which is positive, and then minus 10 pi square root of 3 over a common denominator of 18. If you write like a minus here and then 10 pi square root of 3 plus 9, you would actually need to take that negative and distribute it through the two terms that's in the numerator and have a little bit of a mistake. So we have plus, the 9 is positive here and it's still here. We have a negative 10 pi square root of 3 and it's still negative 10 pi square root of 3. And that is the equation of our normal line. So for a visualization there, we have our sine wave coming through. The sine of negative pi is 0. The sine of negative pi over 2 is negative 1. The sine of 0 is 0. The sine of pi over 2 is 1, and so on and so on. And if you enter this into your calculator, say as y sub 1, and then enter this into your calculator as y sub 2 and y sub 3, well, and maybe I have, of course, the sine function in blue. We're going to see that sine wave coming through, and then here comes the equation of the tangent line coming through, and my drawing's a little bit messed up, but we have a point of tangency at, of course, theta is equal to pi over 5 pi over 6, or the full coordinate of that point, which is the point of tangency, which is 5 pi over 6 and 1/2. And then you have that normal line, which is intersecting the sine wave, but with a slope which is an opposite reciprocal of the instantaneous rate of change of sine when theta is equal to 5 pi over 6. Now, I was kind of doing like I really tried to make this a pretty decent graph without the aid of technology, which I have Desmos on my iPad and this picture already set up, but you might look at something here. Actually, the amount of separation that I have between the sine wave and the tangent line is actually slightly exaggerated here. So we have an area of the sine wave that may be almost indistinguishable between the tangent line and the sine wave. And indeed, when you're close to, and if you take that calculator and start zooming in closer and closer and closer to that point of tangency, you might zoom in so much that you can't tell the difference for a bit of the domain a little bit to the left and right of the point of tangency. You won't be able to tell the difference between the slope of the line and the slope of the function at that value. Indeed, that's exactly kind of what's going on as we go through the derivative process. But you can also then estimate the values of y. So there's this idea called linearization, where we can use a linear function, a line, to estimate not just the slope of a function near a point of tangency, but actually its value as well. That's one way you use tangent lines in calculus. Another way that you use tangent lines is something called Newton's method, where you're approximating zeros. So we have, like, say we have an x-intercept here, and maybe it's such that we can't actually find the x-intercept because the function's too complicated. Well, we can take this idea of Newton methods with some small points and come up with some tangent lines that will, working with the tangent line, we can start, you know, hitting around that x-axis and estimate the x-intercept of our function using tangent lines. And it's probably going to be a series of small steps of building new tangent lines on top of other ones. It's called Newton's method. There's also the Euler's method, spelled E-U-L-E-R-S. Euler's method, I always want to say it's Euler's. Euler's method, which is a way of estimating the solution to a differential equation. Maybe if you, and this is way beyond where we're at right now in calculus, but we're eventually going to learn how to solve a few types of differential equations. Well, differential equations can be quite difficult and maybe impossible to solve. So we can use a series of taking small steps and creating tangent lines along the way, or just lines to estimate the shape. So we'll be able to estimate the shape of a solution, or estimate the function, with something called Euler's method for a differential equation. So even though it's just the equation of a line, something we've known how to do and build or create since Algebra 1, it still has some really powerful applications in calculus. In the description below, I'll put links to those lessons so you can get ahead maybe and just kind of see how all this is going to play out. But for now, I'm Mr. True. Bam! Go do your homework.